Good morning, students. This is your teacher, Mr. Swan. A couple days ago, when we first were going over our syllabus, I remember telling you that if I was sick throughout the year, that I would be doing a screencast for you and have some work for you to do on your Google Classroom. I didn't realize, though, at the time that how quickly that was going to happen. But over the weekend, my daughter came home and was sick on about Friday night, and then turns out she was positive for COVID. And then now I too am also positive for COVID, which has also turned into laryngitis. So I'll be out probably for the week. But a long time ago, I did talk about your education was important, and that point still stands. So I'm doing a screencast for you, and let's get started. Today, I'll be going over a couple topics in our notes so we don't fall behind, including scientific notation, light years, some just general galaxy, universe, solar system information, and we'll go over one of your charts in your reference table. After that, I have a scientific notation worksheet for you to do, and then a small reading, and then you'll be good and done for the day. So let's go ahead and get started. I probably will save the scientific notation for the end. So let's jump on over to light year versus year. Light year and year, two totally different things. Now, there's a big issue when talking about light years and years is that little term, year, right in there. Sometimes when people hear the word year, they think time, which is totally fine. A year is the period about 365.25 solar days required for one revolution of the Earth around the sun. You are about 15 or so years old. So, on throughout your life, the Earth has revolved around the sun about 15 times. I'll come back for that little quarter in a second. Now, light year is a little bit different. Light year is talking about distance, not time. The time would always be a year, but it's the amount of distance that's important. So, light year is the amount of distance light will travel in 1 year. It's a lot. It's this much. This is millions, billions, trillions, right? So, that's about roughly 6 trillion miles a year. That's far. Can't deny. I also put it down here in metric for you. And the good news is you don't need to memorize it at all. All you need to know is that it's really far. And that is the distance that light travels in 1 year. And it's incredibly, incredibly far. And it goes incredibly, incredibly fast. I mean, to go that many miles in a year, it's really got to be cruising right along. So that's usually what people kind of think. Like light years travels really fast. But I also wanted to bring up a little picture. This one. A picture of the sun and a picture of our Earth. It's about 93 million miles away, which we'll talk about a little bit later. And light travels from here all the way across to Earth. It takes roughly 8 minutes for light to travel from the sun to the Earth. Now, we talked about like the speed of light. The speed of light's really, really, really fast. But also, space is really, really, really big. So even though light travels really, really fast, it also has to cover an incredible, incredible amount of distance. 93 million miles is a long, long distance before it hits the Earth. It takes roughly about 8 minutes to do so. And so this is my scale representation of where our sun's located and where Earth is located. So to help you really get a good understanding of how long it really takes for a little bit of light to travel that distance, I'm going to draw a line from right over here by the sun, going all the way over to the Earth, and I'm going to take 8 minutes to do so. We'll do this in silence. We'll start now. Just kidding. That was about 6 seconds. It might have felt like an eternity to you. To give you a sense of scale, it takes light an incredibly, incredibly long amount of time to go from the sun over to the Earth. 8 minutes is a long, long time for light to travel. Heading on back. Over here on the other side, and some of you might already know, that our days don't really line up perfectly. When our Earth revolves around the sun, it does take 365, but it's not quite perfect. It actually does take just like a little bit extra, and that's that quarter of a day. So, how do we live our lives with calendars in a quarter of a day? Well, what we decided to do was ignore it. And so we do. Now we wait 2 years, that 0.25 becomes 0.50. And what do we do then? We ignore it. 3 years, we wait, and then it goes to 0.75 and we ignore it. And then finally, on the fourth year, it's in essence added one extra day over those 4 years, and that becomes a leap year. And leap years are on February 29th. So that's why on some years you have them and some years that you don't. Taking a look at our general object size relationships, this is just kind of to kick us off when we start talking about universes and galaxies. What's the biggest? Well, the number one biggest right now is the universe. There's only one as far as we can tell. There has been a lot of talk about the metaverse, but as of right now that we can prove, there is just only one. In that one universe, there is a massive, massive amount of galaxies. I won't even try to pretend like I know how many. Nobody does. It's just an unbelievably large number. Now, in all those galaxies combined, there are an incredible, incredible amount of solar systems. A solar system is any object that revolves around a star. So for our solar system, you have our 8 planets and they revolve around our sun. So anything that happens to revolve around our sun is a part of our solar system. Whether it takes like 1 year to do that, 2 years, 10 years, 100 years, thousands of years. There's actually rocks that take thousands of years to revolve around the sun. Inside those, next biggest objects are usually the stars. After that, there are a whole bunch of planets. How many planets are there out there? An incredible amount. How many we ever found? Pushing like 4 or 5,000. In there, underneath the planets, you have moons, which eventually will orbit usually a planet. And then eventually the rocks go even smaller to like asteroids, and then even smaller than that. So here's my space objects important information size. And let's take a look at what we got. So we really kind of start off with our universe, and these are numbers that you actually need to know. They're not written anywhere in your reference table, so you do actually need to you do need to memorize these ones. Our universe, the currently observable size is roughly about 46 billion light years across. It formed about 13.75 billion years ago. That's the one that you need to know. If you want, you can round that to 14 if it makes it an easier number for you to memorize. Go for it, and it contains all known matter. Galaxies, I mean, the galaxy that we really care about the most right now to kind of start it off is the Milky Way galaxy. The Milky Way galaxy is believed to be a barred spiral galaxy. And I have a picture of a barred spiral galaxy for you on the very bottom. I would like to show you a picture of our actual galaxy. I cannot. It does not exist. I can show you pictures of pieces of our actual galaxy, but that's about it. So this galaxy that's a picture of, that's not actually ours. They believe it looks something kind of like this. And a barred spiral galaxy usually has like these two really, really big arms kind of going out from the center of it. So that's what it is. Now our galaxy probably has more than just two. And we were actually on like a very small arm that would kind of extend out to like something like right about over to there. So why can't I get you a picture of our actual galaxy? Is it because I'm lazy? Well, yes, but no, that's not the actual real reason. The real reason is because to get a picture of your galaxy, you have to leave your galaxy, turn around, and then take your picture. We have never left our galaxy before. We have never even come close. We sent out radio waves by accident, if this is Earth, a really, really long, long time ago. And those radio waves travel at the speed of light. And they have probably gone out to roughly about maybe 1 or 2 pixels, possibly in size on that map. So my circle I just drew is way too big. So even like the stuff that we sent out at the speed of light, pushing the dawn of radio like 100 years ago, still has not made it their way all the way across our galaxy. So we've never explored it. So that's just the problem. Maybe one day we'll have a picture of it. Probably, though, not in our lifetime. How many stars in a galaxy? Well, nobody knows. Every year, I actually had to update this one on some of the newer best estimates. And they think it's roughly maybe about 300 billion, plus or minus 100 billion. That's a pretty big range. It is what it is. So we'll just say a lot. Now, when this galaxy formed, it formed about 13.2 billion years ago. That's just like a little bit right after our universe formed. We'll do the Big Bang later on in the unit, but right now they formed us like roughly, 600 or so million years right after the Big Bang. That's not too far from the origin. There are thousands and thousands of discovered planets. Those are exoplanets. We'll talk about those a little bit later in the unit as well. And again, there's no full true pictures of the Milky Way. So what do you really need to know? You need to know those times. So the order of formation. I'll draw another one, circle up here. Our solar system formed about 4.6 billion years ago. So that's like way after the universe formed, pushing about 10 billion years or so. Our Earth formed at the same time of our solar system. That's also 4.6. And that includes pretty much like everything in it. We'll talk about that formation and some of the neat mysteries about that a little bit later in the unit as well. So you need to know that formed about 14 billion years ago. Galaxy came next, relatively recent. And then after that, we formed about 4.6 billion years ago. Plus or minus, probably just a tinge. A picture of our solar system. I like this one. And just because it shows that like our solar system is constantly changing. There are things being added and things being removed. Rock that comes in and gets captured by the sun's gravity. Rock that is not really be captured by the sun's gravity anymore, maybe collides with a planet. And there's more and more to be discovered, but it's hard to get out there because space is again so vast. So let's get out something. You need your reference table, and we'll just do two more slides, and we'll call it a day. So I'll give you, I don't know, like 10 seconds or so to go ahead and pull those out. Maybe the sub will pause this video as everybody gets ready. And you want to go to page 15 of your reference table. All right. Well, I hope everybody has their reference table back out, and let's take a look. So, what do we need to know about the planets? Individually and knowing some good information about them is very, very helpful, but we need to classify them first into the major categories. And some of the words that you need to know and the vocab that you need to know about that are right here: terrestrial and rocky. Two words that just really mean the same thing. And then our last four planets are Jovian and gas giants. Again, two different words that mean the same thing. Sometimes terrestrial is written and sometimes gas giants is written, sometimes Jovian is written, sometimes rocky planets are written. So it's always really good to know each one. How to remember these? Terra, like Terra, um, like a nickname for Earth, or extraterrestrial, like ET. It was a good movie a long time ago. So extra, like not from our from here, and terrestrial, like from another planet. So that's where that name comes from. And those planets are rocky. And Jovian and gas giants. I remember Jovian because it kind of looks like the word jovial, and jovial means happy. And I always kind of imagine that the gas giants are really, really big and happy planets. Like back in this photo, look how happy these planets are. They're very joyous at this time. Let's go take a look at that. I'll save asteroids, comets, and meteors. We'll do those a different day. So on page 15 of your reference table, hopefully you're open to that by now. This is some data about all those planets. And I briefly showed it to you that first day. But what I would like you to do is take out a pen or pencil, totally up to you, and write right in here, terrestrial. And write right over here for these four planets, Jovian. Go ahead. I'll give you like 15, 20 seconds to go ahead and do that. All right. So hopefully you have that. So the neat part is that those terrestrial planets formed right near the sun. Not an accident. Those gas giants formed very, very far away from the sun. Also not an accident. We'll talk about that too in the formation of the universe. Over here on the chart, it has like the sun right here on the top. And the first column is mean distance from the sun. So the average distance in millions of kilometers from the sun. So Mercury is not 57.9 kilometers, it's 57,900,000 kilometers away from the sun. Venus, 108 million, and then so on. And you can see how far these scale out as it gets as they get bigger. Period of revolution. We'll talk about some of these terms again another day. But period of revolution, it means the time that it takes an object to orbit around another one. So Mercury actually orbits relatively quickly, 88 days. So 1 year on Mercury would be roughly about 3 months worth of time on Earth. So if you're 15 right now and you happen to be born on Mercury, you'd be considered 60. Venus, about 224 days. Earth is our 365. That's where we get our term for our year. Mars is about 2 Earth years. Jupiter is about 12 or so Earth years. So in your lifetime, you've watched Jupiter orbit around the sun one time. Saturn is 29.5. So I've seen Saturn orbit around the sun one time in my entire life. Uranus is 84. I would hope to see Uranus orbit around the sun at least once in my lifetime. And Neptune takes 164. Not really feeling that one. Such is life. Period of rotation is how long does it take a object to spin on its axis one time. So for Earth, it takes roughly about 24 hours. That's what it is right here. As you might notice, that does not say 24 hours. We'll have to talk about that when we talk about Earth's motions. But Earth's motions are actually unit 2. So that time will come. But it's all based upon its orientation to the stars. And because we're moving and our galaxy is rotating and as well. Venus is a special planet for its rotation. It takes 243 days to rotate once. So Venus is the only one where it takes longer to rotate on its axis one single time than it does for it to revolve around the sun. The rest of them take 24. Mars takes 24 hours, a little bit longer than us. Jupiter is slower. The Saturn is bigger. Uranus is longer. Then Uranus is even longer, and then Neptune's a little shorter. So, general trends is that distance from the sun and rotation doesn't have any kind of correlation whatsoever. While period of revolution, though, as you can tell, as you get further away from the sun, it takes longer and longer for objects to actually go around. So I like to think about that as when you're doing everyone's favorite activity when you're not in science, doing the mile in gym, and you're going around that track, right? And they probably give you an option, like what does everybody do? Do they run in the inside circle, right? Or are they running like on that like longer oval on the outside? Well, everybody probably goes right around to the inside, right? Because it takes a shorter distance to go around. I think it's 4 times around the track for a mile, about 4 times to go right around. Or you could go on the outside if you really wanted to, but it would take you longer to do those same amount of, we'll say, orbits. And so it's really two reasons as well. Because somebody say, well, is it speed difference? Is Mercury faster? Mercury is faster. And Neptune actually is slower. That actually also does correlate with distance from the sun, but it's also the distance, the sheer amount of distance they have to travel as well. Eccentricity, that's going to be a unit 2 thing. So we'll come back to that one. Equatorial diameter just means how big is the diameter of our planet. Well, the sun's diameter is very, very big. Well, Earth's diameter, not so big. Distance from sun doesn't seem to correlate whatsoever. But our rocky planets are very, very small, while our gas giants, again, are very, very, very big. Mass. We talked a long time ago about like measurement systems. And I like measurement systems because I think they're funny. But this was another one. Like how do you weigh a planet? And the answer is, well, that's too hard. So let's just make up a new system. And so let's call Earth equals 1. So Earth is our base standard. And we compare everything then to Earth, right? So Mercury is a fraction of the mass, pushing like a 20th. Venus is pretty close. Mars is like a 10th. for sheer mass. And Jupiter is just ginormously huge at more than 300 times bigger. So its gravity is incredibly immense. And then that goes into density as well. For our rocky planets, they are more dense. And then for our gas giants, they are less dense. This density is grams over cubic centimeters. So it's all based off of water. So water is roughly 1. And if you were, maybe you've heard the term before, but if you put like, I don't know, Earth like in some kind of ginormous ocean, it would sink because that number is greater than 1. But on the other hand, Saturn, if you put Saturn on some type of ocean or water source, it would float because it is less than 1. And the bottom is Earth's moon. I usually save Earth's moon for unit 2 because there's a lot of tricky stuff about Earth's moon. So we'll get back to that a different day. That's our second to last slide. So let's go and go back just to look a little bit, and let's just do a quick little thing on scientific notation. We're going to use scientific notation quite a bit because like you're going to have to write out a lot of these numbers. And so imagine trying to write out 5,878,000,000,000 and so on miles per year for light when you could abbreviate it, and it's really that abbreviation is what we're going after. So for this part, I have some examples, and I'll jump on another page to show you other examples as well. But scientific notation really is just a simple way of showing a number and a multiplier of 10. And it'd probably be too long to be written out in a normal way, such as our sun is 93 million miles away. In scientific notation, you write 9.3 times 10 to the 7th. Well, how does this work? So let's make a new number. How about I do like 40,000? All right. So on the number 40,000, and a lot of times when you write numbers in math that are, whole numbers, positive numbers, there's no decimal written in there. It's just implied that it would be on the far right side. So sometimes it can help to go ahead and put that in there on a positive number, that the decimal should be on the far right side if it's not listed. And that's what the first bullet point is saying. So put a decimal to the right of the first whole number and write down the number that after it. So this becomes number dot number. So that part is saying you need to move this decimal to there, to the right of the first whole number. So that's a 4. And you can write 4.0 if you want. You can also write 4. That's probably also technically acceptable. And then what we always keep for scientific notation is that times 10. That never changes. So you always keep that. So it's times 10. And then you count how many spaces that you moved. So I moved 1, 2, 3, 4. And then you write that number of times it moved up here, and that's your exponent. So that's 4.0 times 10 to the 4th. All right. I'll show you a couple of other examples, and we'll do really small numbers as well. So let's say we do, how about 63,000? Why not? We'll do the same thing. All right. So to make that into a smaller number, I got to get my decimal. So that's got to be on the far right side. And I got to move that to the right of the first non-zero number, right? The first whole number. So that's going to be the 6. So it's going to go 1, 2, 3, 4. And so then you want to write that. You want to write the 6. And you don't want to drop off the numbers that are non-zeros, right? So it has a 3 right there. I want to keep that 3. So it becomes 6.3. And then times, and it's moved 1, 2, 3, 4 more spots. So times 10 to the 4th. How about if you had something like really strange? Like how about 5, 6, 7, and let's just put a whole bunch of zeros on there. All right, so a huge number, right? So that's pushing into the billions. What do you want to do? Same thing. Nothing changes. Once they have the pattern always stays. You got to put the decimal where it has to be if it's not already in the number, and you got to move that to the right of the first non-zero number. So in this case, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So that becomes 5.67 times 10 to the 10 to the ninth. I still feel free to do the same. Still draw these like little squiggles under the bigger numbers when I'm doing it. I find it very helpful. Personal opinion. So let's do how about a really small number instead of a huge large number. So how about something that's like really tiny, like 0.00003. The same rules apply. You have your decimal. This one happens to already be written, but you got to put it to the right of the first non-zero number that you see, reading from left to right. And then you got to move the decimal over to do so. So 1, 2, 3, 4, 5. So that becomes 3. You can write 3.0 or just 3 if you want, times 10. And I moved it 1, 2, 3, 4, 5. I moved it 5 spaces. Now, the issue is that instead of moving it from the right side of the number to the left side of the number for a really big number, I'm trying to show that this is a very small number. So instead of doing that, from moving from the right to the left, we moved it from the left side to the right side. We signify that with a negative sign. And that's it. So in science versus math, there's and pretty much in 10th grade and kind of going on, you're going to come up to a little bit of a difference in science where negatives don't mean like an unreal negative number, like negative 2 apples, which can't exist, that kind of thing, right? Negatives in science mean this. Are you ready? Negatives in science show direction. Negatives in science show direction. That's it. You'll use that phrase if you go on to science for the rest of your entire life. It's going to be really, really helpful. It just shows that instead of going in one direction, the negative means you went in the opposite. All right. Sounds good. And if you want to go backwards from one of these, well, you do the same thing. So if you have 3 times 10 to the negative fifth, well, that means you got to make a really small number. So you got to move that decimal 1, 2, 3, 4, 5. So the decimal goes right there. And then every time you move to space, you got to put in a 0. And there you go. We get the same number backwards. Sounds good? Well, best way to learn scientific notation is not really to listen to me talk about it, is to go ahead and do it. So I made you, believe it or not, a very special worksheet. These are all true, semi discussing true facts, but all true facts for you to help you learn scientific notation. So I'll have the sub pass those sheets on out. I'll give you guys like a little while to go ahead and do that. And then the sub will go over the answer key, and you guys will all do it together. I believe then one more reading in your Google Classroom, and you'll be all set for today. Well, I hope you enjoyed the first of our many screencasts coming together. Have a great afternoon. If you have any questions, feel free to email me. I monitor it all day long. All right. Have a good day. Goodbye.